So is my screen visible to all of you? Is my screen visible to all of you? Can anyone answer?
Yes, visible.
Okay, thanks. Okay, so good afternoon, good evening, all of you. So today we are going to discuss about the week 2 session about Introductory Organic Chemistry Part 2, which is a NPTEL platform course. And the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. And I am Simran, your PMRF teaching assistant. So we have talked about the NMR questions in the week 1. So the lecture is uploaded on the YouTube channel. You can go through that. And if you have any problem regarding the last lecture, please let me know. So any one of you have any problem regarding the previous session? Anyone has questions about that? Or should I start with the week 2 lecture? Okay, so it seems like no one has any doubt regarding the previous session. So I'm starting with week 2. So, guys, today's topic is electrophilic and nucleophilic aromatic substitutions, and some part is taken by the IR spectroscopy also. So, today we are going to discuss about the electrophilic and nucleophilic aromatic substitutions. So, coming to the problem number 1. So, they are asking the order of reactivity in the following series of compounds in which X denotes the substituent. So, this X is denoting the substituent, like which is mentioned in our options. These are some substituent which is X. So they are asking the order of reactivity in the following series of compounds towards the nucleophilic aromatic substitution. So this is the nucleophilic aromatic substitution reaction, and what substituent should be there you have to identify. So here you have to identify the order of reactivity towards nucleophilic aromatic substitution. So, can anyone tell me which will react faster in nucleophilic aromatic substitution? Okay, so what will happen in nucleophilic aromatic substitution? So, first of all, we need to know the mechanism. So, how the nucleophilic substitution is going on, you have to know that first. So, this is a basic reaction of nucleophilic aromatic substitution. So, here in the aromatic ring, here the nucleophile will attack, and there is a leaving group that is present on the aromatic ring which will leaves out. So the mechanism will follow this path. Here a sigma complex, that is a mesenheimer complex, will get formed. So first of all, nucleophile with electron density will attack on the benzene ring, and then a negative charge will then generate at the adjacent carbon to which the nucleophile is getting attached. So here this negative charge is delocalized in this particular ring, and here a mesenheimer complex is getting formed. So this is a sigma complex. So here what will happen next? Now this nucleophile like this is attaching here, and this leaving group X will leaves out. This negative charge will come here, and now this X group that is here will leaves out to give you again the aromatized system. And now your nucleophile is substituting your leaving group. So here this nucleophilic aromatic substitution means here the nucleophile is substituting your leaving group. So now what will happen? First of all, this addition will take place, and then substitution of the nucleophile by substitution of the halogen by the nucleophile. Okay. So coming to the question back, so here they're asking the order of reactivity. So now you need that series of compounds in which the negative charge is getting stabilized on the ring. So here after the formation of this, they are asking that if your nucleophile, that is this proline in this case, if it is attacking on this carbon and leaving out this fluoride, then what will happen? A negative charge is getting generated on the benzene ring, right? So now you have to identify which of the following compound, that nitro, cyano, which of the following group will act faster in nucleophilic aromatic substitution. So here, if cyano, nitro, and COMe, these are some groups which are attached at this the para position of the fluorine. So here, if nitro and cyano, they are going to attach at X. So if they are X, then the reactivity order will depend on the stability of the carbon ion that is generated in the system. So higher the stability of that negative charge by the group, higher will be the order of reactivity. So here the negative charge is stabilized more by, so based on this concept which I have told you, so which would be the answer? Like which option should be right? Can anyone tell me? As you know, the group which is stabilizing the negative charge more will increase the reactivity towards the nucleophilic aromatic substitution. So which will be the group which is stabilizing the more this particular negative charge which is generated on benzene ring? Anyone? Any guesses?
Cyanide, I guess.
Nitro group.
Sorry, nitro. So nitro group will be the highest reactivity group because nitro is having highest electron withdrawing ability. So after that, cyano is having the highest electron withdrawing ability. So based on the electron withdrawing groups, the electron withdrawing groups will stabilize the Mesenheimer complex that is formed here. So here the the basic concept is higher is the stability of this negative charge, higher will be the reactivity towards the substitution. So Mesenheimer complex has to be stabilized. So stabilizing group contains like electron withdrawing group. So more the electron withdrawing group is, more is the stability of that negative charge. So here, now tell me what will be the order of reactivity, which is the correct option?
Option A.
Option A. Any other answer than option A? Okay, so clearly you have to know that which will be the most electron withdrawing group. So nitro is much more electron withdrawing than cyano, and cyano is much more electron withdrawing than this acyl group. So here and methyl, you know that it is the least electron withdrawing group. So part A is the correct option. Higher is the stability of the Mesenheimer complex, higher will be the reactivity of the compound towards the nucleophilic aromatic substitution. So this is the concept which you have to learn in this particular question. Okay. So is it clear to everyone, or should I repeat? Is it clear to everyone? Okay. So if it is clear, then I'm going to next problem, that is problem number 2. So in the problem number 2, they are asking which of the following mechanisms of action occur when there are electron withdrawing group on aromatic ring during nucleophilic substitution. So they are asking that during nucleophilic substitution, if the ring is containing the electron withdrawing group, then which pathway of mechanism is to follow? Is it the addition elimination? Is it the elimination addition? Is it the substitution addition or addition of substitution? So the answer of this question is hidden in the problem number 1 itself. So can anyone tell me which pathway is operative?
Addition, elimination.
Addition elimination. So here you can say that addition elimination, there is a actually hidden concept between this addition elimination and this addition substitution. So guys, what is happening? First of all, it is clear that addition is happening of the nucleophile, right? And then what is happening at net? Elimination or substitution? Is nucleophile substituting the new leaving group, or what is happening? So here in this reaction, you can say that first of all the addition of nucleophile is taking place, and after that the substitution of nucleophile, sorry, substitution of the leaving group by the nucleophile is going to take place, right? So in the net you can say that addition and substitution is taking place rather than the elimination. Elimination of course is taking place, but the rate determining step is the addition substitution, right? So particularly you have to answer it like addition and substitution. Is it clear to everyone?
Yeah, ma'am.
Okay. Then I'm going to problem number 3. See, yeah. See, you can see here also that first of all, nucleophile is getting attacked over this benzene ring, and then what will happen? A Mesenheimer complex will form, and after that, what will happen? That negative charge comes back, and you have this Cl eliminated. But the net is your nucleophile is replacing your leaving group, right? So leaving group is getting replaced by the nucleophile. That is why we are saying that the substitution of leaving group is taking place, right? So there is a addition and substitution mechanism which is operative in this case. So now coming to problem number 3. So they are asking the major product of the following reaction is. So they are asking that the major product of this reaction. So what is happening in the reaction? They have added a Lewis acid. So if they have added a Lewis acid, what it will do? It will chelate with your carbonyls of this acetic anhydride. So this acetic anhydride will chelate with this Lewis acid, and now what will happen? That it is becoming more electrophilic in nature, right? So this species is now chelating with your aluminium and the groups which is attached to it. Okay, right? So there is a chelation, and now your electrophilic character of this carbonyl carbon is getting increased, right? So now what will happen next? Tell me what will happen next. If there is an electrophile in the system, then what will happen? So if you have a electrophile here, then what will happen, guys? You have a methoxy group, and everyone knows this methoxy group is electron releasing group, right? So if methoxy group is electron releasing in nature, then the reaction is what? Electrophilic substitution reaction or nucleophilic substitution reaction? Which is this reaction? Electrophilic substitution or nucleophilic?
Electrophilic.
Electrophilic. So here you have a electrophile in the system, and here this ring now behaves as a nucleophile rather than the electrophile which we are seeing in the 3 cases. Here the ring is acting as nucleophile. Why? Because it is having electron releasing group attached on the ring. That is why now your ring is electron rich in nature. So now this lone pair of methoxy will come down, and now it will attack to this particular acyl ion, which will leaves out this acetate. So now this COCH3 is getting attacked on this particular benzene ring. So now tell me at which position this acyl group will attach on this benzene ring.
Ortho position.
Ortho. Okay. Any other answer? Option number, just tell me the option number which is correct. What do you think? So someone is saying that ortho position, that is A. Next,
Para substituted.
para, that is C. Okay. So as we know that this fluorine and methoxy group both are ortho para directing, right? Because they are electron releasing. So guys, what will happen? The most activating group is wins, because what will happen here, your strong activating group, that is the methoxy group, is present, and here in our case the weak activating group is fluorine. So here fluorine is present. So now if we are comparing this methyl and methoxy, if we are, just forget about the question, and we are comparing this methyl and methoxy, so here we have to see which is more activating. So methoxy in turn is more activating than methyl. So now it will direct the upcoming group. So upcoming group is directed by the strong activating group, right? Rather than the weak activating group. So now if it is orthopara directing and methyl is also a weak activating group, that is a orthopara directing. So now what will happen? This ortho position is getting activated, or this ortho position is getting activated. So this methoxy group, if it is stronger enough, then it will activate the position which is close to it. That is the ortho position, right? Because at para position methyl is present, so it is blocked position. So nucleophile cannot come here, and same as for methyl, methoxy is occupying the para position. So now nucleophile is not going to come at para position for both the cases because they are blocked. So now the competition is in between the ortho positions. So methoxy ortho position and methyl ortho position, so you have to worry about the two things. So now, if there is a competition between the upcoming group, uh, then what will happen? The stronger activating group will direct the upcoming group. So here, our methoxy will direct the upcoming group. So it will direct the chlorine at the ortho position, which is closer to methoxy group rather than the methyl ortho position. So here you will get this compound and not this compound. So that is why you have to listen to stronger activating group. So that will direct your electrophile. Okay. So is it clear? This particular example of methoxy and methyl, why this compound is getting formed and not this?
Yes, ma'am.
Okay. Now, if it is clear, then coming to this particular problem. So here there is a simple problem. So now our question is also saying something like this: methoxy and halogen atom. So here, methoxy and halogen atom. So I have told you that in between the methoxy and halogen atom, which is more activating group? Yes,
Methoxy.
methoxy is more activating. So both of them are showing the orthopara directing effect. But what happened? You have to see which is the more activated uh, group. So now in our case, methoxy is strong activating group, and now there are how many positions? Three positions which could be possible for the attachment of the electrophile. Why? Because methoxy have orthopara position, that is ortho and para, and again your Br have orthopara position, that is ortho and para. So three possible positions are there. So which will be dominating? Methoxy, right? So now methoxy will direct the group at para position more, because we have seen if there is a competition between ortho and para group to be formed. So we have seen that para group is formed more than ortho. So para product is major product than the ortho product, because para product is more stabilized than ortho. We have seen this in electrophilic substitution reactions, right? So we know that para product is more in concentration when there is a competition between ortho and para, right? So that is why now your group is going at para position, which is also ortho to Br. Okay, so that is why your group is going at this para position. So there is a question which is coming in the mind, why the Br para position is not activated, because we can also say na that at this position I am placing this R group. It is also a ortho position for methoxy and para position for Br. But now we are saying that which is more activated, that has to be the deciding factor. So now methoxy is a deciding factor. So here methoxy will find a para position more favorable for the attachment. That is why your this position is getting activated rather than the rest of the two. So you are getting this product, not this product. Is it clear to all of you why we are ruling out C and D and B as well? So formation of A is going to be happen. So is it clear for this case? Any query, guys? Okay, if there is no question, then coming back to the question. So now what they are asking is the major product of the following reaction. Now quickly tell me which will be the correct answer.
C.
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 Option number C will be the correct answer. Okay. So C will be the correct option, right? So now coming to problem number 4. So problem number 4 says the increasing order of reactivity of the following compounds towards electrophilic aromatic substitution is. So now again you have to arrange it in the increasing order of reactivity towards electrophilic aromatic substitution. So can anyone tell me which will be the correct answer? Just think about the electrophilic substitution mechanism and you will get the answer. Okay. So I'm showing you here the mechanism of electrophilic aromatic substitution. So guys, what will happen? The benzene ring is reacting as a nucleophile here, right? It is acting as a nucleophile. Fine. So now it will trap the electrophile. So while trapping electrophile, a positive charge is getting generated on the benzene ring, right? So here the positive charge is stabilized by the conjugation. Again, there is a proton abstraction, and here rearomatization will take place, right? To get back this particular substituted aromatic ring. So this is what the mechanism looks like. So here there is a positive charge that is going to generate on the benzene ring rather than the negative charge which we have seen in the nucleophilic aromatic substitution case. So now coming back to the question. Now quickly tell me which is the correct option. You have to arrange them in the increasing order of reactivity. So one by one, I think I have to answer this. So one by one, we are going. See, first of all, come to fourth option. You are having a aldehyde group at the substituted position. So now you are knowing that this particular electrophilic aromatic substitution going through a positive charge formation on the ring. So is the positive charge stabilized when electron withdrawing group is present or electron releasing group is present? Which group is going to stabilize the positive charge?
Electron withdrawing.
I'm saying about the positive charge, right?
Donating.
Yeah, electron releasing group or electron donating group will stabilize your carbocation very quickly, not the electron withdrawing. See, it is already electron deficient na, the ring is already electron deficient and you are withdrawing electrons, then how come that will be stable? So that is why here the ring is electron deficient. So you need electron releasing group to stabilize that particular ring. So here this fourth option, it is having the strongest electron withdrawing group which is attached. So now it is highly reactive or least reactive to the electrophilic aromatic substitution. Which is this? Least reactive or highly reactive?
Least reactive.
Least reactive. So it is clear that fourth option is least reactive. So you are left with two option only because fourth is coming at in two option at the least, right? So now coming at 1, 2 and 3. So now tell me the second group which is least reactive. Least reactive after 4. I mean before 4, sorry. So which one?
Fluorobenzyl.
Third.
Third one.
Because fluorine is also,
Deactivating group.
yeah. So fluorine is also here the, it is showing the electron releasing ability, but it is also showing the minus I effect due to the electronegative nature of the fluorine atom. So that is why it is also considered as the withdrawing the electron density from the ring. So that is why the third option will come. So now these two option is having 4 and 3. Now the race is between first and 2. So first and second, tell me which will be the more reactive. First will be more reactive or second will be more reactive?
Second.
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 So why you people are thinking second? See,
Fourth position for positive charge.
fourth position positive charge. Okay. But guys, you have to think about that point also. If nucleophile is getting attached at this position, just tell me that if nucleophile is getting attached at this position, right? Then also it is going to form a positive charge here or positive charge here. And if nucleophile is going to attach at this position, then it is going to form a positive charge here and a positive charge here. Which is more stabilized, first and second?
First.
Yeah, first is more stabilized because as soon as the positive charge is getting generated, it is stabilized by the electron releasing group. So here the methyl group is stabilizing the positive charge. But here, as you can see, the reactivity is close enough. I'm not saying that first is much more reactive than second. The reactivity is close enough because two methyl groups are present in the ring. And due to the conjugation, the positive charge also resonates. But if you see, the first addition of nucleophile will generate the positive charge, and that positive charge is much more stabilized in the option number 1 rather than option number 2. Agree with me?
Yes, ma'am.
Yeah, so that is why this first will be the higher reactivity group. That is why the option number which two or third, which is correct, the option number 2 will be the correct one. So
Correct.
here first will be the higher reactivity compound, then second, then third, and then fourth. Right? So is it clear to all of you the trend? So if it is clear, then I am moving to problem number 5. So now in the problem number 5, they are saying the following reaction yields what? So now you have to identify the product of the following reaction. So this is the reaction and you have to identify the product. What is sodamide here? Sodium amide, what will it do? Is it an acid or a base?
Base.
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 Yeah. So sodium having the positive charge, NH2 is having a designic base. Fine. Negative charge. So what will base do? So
Proton abstract.
yeah, it will abstract a proton. So guys, whenever you have a base, strong base in the medium, first of all the thing which it will do is the abstraction of the proton. acidic proton. So now they have three options to abstract the proton. So now tell me that which of the, like, four options are there, no? So which of the proton is more acidic? Proton attached adjacent to OMe or proton attached adjacent to Cl?
Adjacent to Cl.
Yeah, adjacent to Cl. So it is much more acidic in nature because of the electronegativity of the chlorine. So the concept of electronegativity, electron releasing group, electron withdrawing group, that will mix up to give you the answer only. Okay, so everything is going to come between these concepts only. So here, as it is a base, it will abstract the proton. So here it will abstracting the proton. So after abstraction of proton, what will generate? A negative charge. So now there is a negative charge which is going to generate. So here there is a negative charge at this carbon. So now what will happen? This is a leaving group. So what will get to form?
Benzene.
Yes. So now it will go here and this leaving group will leaves out to give you a benzyne intermediate. What is benzyne? This is benzyne. So this is benzyne. Right? So at one position you are having this OMe and Cl is going leaves out. So you have this triple bond of benzyne with you and a conjugated ring. Right? So this is how benzyne looks like. So now after the formation of benzyne, the next thing is, as you have added a excess of NaH2, after behaving as a base, now what it will do? It will behave as a,
nucleophile,
yeah,
Nucleophile.
it is behaving now as a nucleophile because you have added it in excess. And now if you have added a base in the system that is a nucleophilic base, then first of all, after doing the job of proton abstraction, it will act as a nucleophile. So now if it is acting a nucleophile, then it has two options: rather to react here or rather to add here. So which will be the operative pathway? Pathway A or pathway B? Tell me which will
A
be
pathway.
pathway B.
path B,
Path B.
B.
Okay. So now we have both the answer, path A and path B. Now just look and see what will happen. It will if it will add at pathway A. So now you are generating a a negative charge at this position, right? And in the pathway B, you are generating a negative charge at position this, adjacent to methoxy group. So now which position is stable position? Now you have to look at which position the carbon ion is stable, adjacent to the methoxy or at the meta position to the methoxy. So so
Meta position.
meta position to methoxy. So now you have to see, you need to know that which is the stabilizing factor of that negative charge. As you have an idea that the methoxy group is electron releasing in nature, so it will
Yes.
stabilize the carbocation rather than the carbon ion, right? So carbon ion will find a way to distant with this particular methoxy. So now if the farther the basically farther the negative charge formation, stability will come there only, because now methoxy is electron releasing and it is also having the electron density with him. So now there is a electron crowding which is happening here. So that is why it is not going to stabilize that carbon anion. If there is a electron withdrawing group that is present instead of the methoxy, like nitrocyano, then the ortho negative charge is getting stabilized. But here negative charge wants to be a distant, a farther apart from the methoxy group rather than the electron withdrawing group. Okay, so that is why your amide, that is NH2, will add at path A or path B now?
Pathway A.
Pathway A. So it will add to pathway A because negative charge wants to be far away from this methoxy group. So that is why the option number A will be the correct option. Is it clear to all of you?
Clear.
Okay. Okay. So here we are seeing some examples. So sodamide and ammonia. So here no strong preference is there. That is why you are going to see the mixture. In the case of CF3, meta will be favored. But here not meta will not be favored. So methoxy, okay. Methoxy also have a electron withdrawing effect. Yeah, will
Inductive effect
yeah.
count.
Yeah, it's also have a inductive effect. That's what I'm missing. So guys, here plus R effect is also there, but minus I effect is also there, na? Plus R, but minus I. So you have to consider on both the things, plus R and minus I. So because of the minus I of oxygen, because of this methoxy minus I, because of the presence of electronegative atom, so now, sorry for the mistake guys, so here also you are going to see both the pathway, but which will be favored, the pathway B. So the correct option will be part A, part B, because of the minus I effect that is also operative here. We are not considering the minus I, na? We have also a minus I effect which is present in the system, so we have to consider that also. So by considering that, the negative charge is now forming at the ortho position and is stabilized by the minus I effect. So that is why this amide will attack on this meta position rather than the ortho position. Is it clear?
Yes.
Okay. So if it is clear, now coming to problem number 6. So they are asking which among the following compound will not react under the standard Friedel-Crafts alkylation reaction condition. So now coming to Friedel-Crafts alkylation. So what will happen in Friedel-Crafts alkylation? So this is the Friedel-Crafts mechanism, guys. So what will happen here? This AlCl3 in the Lewis acid in this Friedel-Crafts alkylation will bind to this leaving group, and there is a positive charge which is getting formed. So now if carbocation has to form, then what will happen? It will forming at this position. In this case, at this position. Now tell me which is the most stabilized carbocation. Which is most stabilized?
Third. Third
C.
option.
Yeah.
Third option.
Yeah. Third is more stabilized. Why? Because of the resonance. Right? It is stabilizing it by the resonance. So here the double bond migrates here to get the positive charge here. So that is why there is a resonance between these. So that is why the third is highly stabilized. Now tell me the least stabilized one, because they are asking which among the following compound will not react under the Friedel-Crafts reaction condition. So the compound which is having the least stabilized carbocation formation will not give you the Friedel-Crafts alkylation. So which will be the correct option?
First.
First. So first is a vinyl radical, which is getting formed, right? So because of the vinyl radical instability, the option number one is not going to give you the Friedel-Crafts alkylation. So now, first of all, guys, in every question, you have to know the mechanism. So mechanism is dictating the answer itself. So if there is electrophilic aromatic substitution, then the presence of electron donating group will uh, mark your uh, mark your answer. And also, if there is a nucleophilic substitution reaction, then the presence of electron withdrawing group is necessary. Similarly, Friedel-Crafts alkylation carbocation generation is taking place, and now for the compound which is not reacting under that condition, you need to know the least stable carbocation formation, and the compound will not give you the Friedel-Crafts alkylation at all, right? So in these all the four cases, the compound one is the one which is forming the least stable carbocation, that is the vinyl carbocation. So here there is a secondary carbocation which is getting generated in both the cases, and second and fourth, but here there is a vinyl carbocation, so that is why it is least stable. So here it will not going to give you the Friedel-Crafts alkylation. So is it clear to all of you why one is not going to give you the Friedel-Crafts alkylation? Anything which is not clear? So if it is clear, then I am moving to problem number 7. Please ask me if there is something which is not clear. Please ask me, I will explain you again. So coming to problem number 7. Why you people are joining so much late here? Okay, so the nucleophilic substitution do not occur in haloarenes because the carbon halogen bond is much shorter, sorry. The carbon halogen bond is stronger compared to haloalkanes. The lone pair of electrons on halogen participate in delocalization, or all of the mentioned. So they are asking why the nucleophilic substitution reaction does not takes place in haloarenes. So you have to give the particular reason for that. So among these options, which is the clear reason for the nucleophilic substitution not happening in haloarenes? So what are haloarenes? Haloarenes are halogen containing groups, right? So these are electron donating group that is attached. So X is electron donating group, some electron donating, OMe, anything. Because they are asking about the nucleophilic substitution, na? That is why you have to think that yes, there is an donating group that is attached, because now it is making the ring nucleophilic. So now they are asking why these haloarenes, halobenzenes, are not going to give you the nucleophilic substitution. Can anyone tell me which will be the correct option? Why they are not giving the nucleophilic substitution readily?
C option.
Three. Option three.
Option C. Any other option? Any other answer?
All of the mentioned.
All of the mentioned. C. Haloalkanes. So what they are mean by haloalkanes? Basically, a methoxy group containing, or any group containing, any releasing group containing this allyl chain. So this allyl chain is able to give you the nucleophilic substitution reaction. But why this haloarenes are not going to give you? See, what will happen if it is a methoxy group? Now there is a conjugation that is present with this particular benzene ring. So negative charge is going to resonate like this. So now coming to one by one on the all the options. Option number A suggesting that haloarenes are having carbon halogen bond is much stronger. So here they are saying that carbon halogen bond are much stronger in the case of haloarene. So is it true? Because they are talking about this carbon halogen bond, right? This carbon halogen bond. So is it much stronger than compared to haloarenes? This is carbon halogen bond. So which is stronger? The single bond or the partially double bond? Which is stronger?
Double bond.
Yeah. So they are claiming that the carbon halogen bond in haloarenes are much stronger than haloalkanes. So now this statement is right or wrong?
Right.
Yeah. Because this statement is right, so option number A is right. Right. Now coming to option number B, the carbon halogen bond is stronger compared to that of haloalkanes. Is it stronger than the single bond? Yes, it is also stronger. Why? Because there is a partial double bond in between the CX bond in haloarenes, whereas in haloalkanes there is a single bond which is less stronger. So part B is also right. Coming to part C, the lone pair of electrons on halogen participate in delocalization with pi electron of benzene ring. Is it right? The lone pair is participating in delocalization. So here it is.
And
Yeah, it is also right. So that is why we can say the option number D is the correct option, because all of the mentioned reasons are the reasons why nucleophilic substitution doesn't take place readily in haloarenes. Okay. So is it clear to everyone why option number D is the correct one?
Yes, ma'am.
Yes.
Okay. If it is clear, then I am coming to problem number 8. So problem number 8 is saying the rate of nucleophilic substitution reactions are higher in the presence of electron withdrawing groups, electron releasing groups, both, and none of the mentioned. Just tell me the correct answer very quickly. I have showed you the mechanism of nucleophilic substitution reaction.
Electron withdrawing group.
Okay. Any other answer than this? So everyone agrees with electron withdrawing group? So yes.
yes, ma'am.
Okay. So here, as I have told you, that nucleophilic substitution reaction means that Mesenheimer complex is getting formed. So here a negative charge is going to form on the benzene ring, right? So negative charge are stabilized or can be stabilized by electron withdrawing group, not by the electron releasing group, right? So that is why we are saying the option number A is the correct one, because electron withdrawing groups are stabilizing these things. See here, the negative charge is getting stabilized by nitro group. That is the electron withdrawing group, right? Okay. So coming to problem number, so I mentioned this slide. Okay. So now it is stabilizing the negative charge which is going to form after the addition of the nucleophile. That is why the electron withdrawing groups are going to give you the readily nucleophilic aromatic substitutions. Fine. So coming to problem number 9. So this is some kind similar kind of question. So problem number 9 is saying which of the following compound shows the correct decreasing order of solvolysis with aqueous ethanol. So now you have to identify the correct decreasing order of solvolysis. Solvolysis meaning, see, in aqueous ethanol, if solvolysis is going to happen, then carbocation formation is taking place. So the CX bond is going to cleave. There is a carbocation which is going to form. So at this carbon, carbocation is getting formed. At this carbon, it is getting formed. So they are asking correct decreasing order of solvolysis. So solvolysis will be facile when the carbocation which is going to form in the solvolysis process is stable enough, right? And it will be least if the carbocation is not going to get stability, right? So now tell me which will be the correct option. I have told
Option B.
option A. Okay.
Option number B.
Option number B. Okay. So now they are asking you the correct decreasing order. Option number B, you are saying, and option number A. Okay. So now here, option number A and B only have the last two things different. So as you can see that here this three option, that is there are tertiary carbocation which is going to form in the third option. In the second option, which will be the order of the carbocation? Second. So it is a secondary carbocation which is going to form. Here a primary carbocation is going to form, and here a tertiary. We have taught. And what is this? This is the vinyl carbocation. And I have told you before that vinyl carbocation is least stable than primary carbocation. So the order is tertiary carbocation, then secondary carbocation, then primary carbocation, and then vinyl carbocation. So vinyl carbocation are least stabilized. So now coming to option number A and B. Option number A is suggesting the third, second, first, and fourth. It is suggesting that first is less stable than vinyl carbocation, but it is not the case because I've told you that vinyl carbocations are least stable than primary carbocation. So, option number B will be the correct one rather than A. So, the order plays tertiary, secondary, primary, and the vinyl. So, is it clear to all of you why A is not the correct option and B is the correct one?
Yes, ma'am.
Okay. So, is it, if it is clear, then I am going to problem number 10. Now we will move quickly. So, here they are asking the major product formed in the following reaction. So, this is a nitration condition. So now you have to identify at what position nitration will be the major. So which will be the correct option? What do you think? Is it the nitro group which is adding? Is it the SO3H group which is adding in this reaction? Sorry,
Nit-
nitro group. So second is getting eliminated. Fourth also is getting eliminated. So now you have competition between 1 and 3 option.
C is the right answer.
3 is the right answer.
First one, first one.
First one is the right answer. Okay, so we have both the options. So guys, so okay, let me tell you here. Now you have to see the preference, but for seeing the preference of both the groups are similar. So now tell me, it is ortho para directing, right? Both. So if we are considering this Cl1, then this is the ortho position, and this is the ortho position, and this is para position, right? So this is para, and this is ortho of chlorine 1. Chlorine 2, this is the ortho position, this is ortho, this is again ortho, and this is para, right? And I have told you many times that para position is the position which is getting the major product formation, right? So for this Cl it is the para position, for this Cl it is the para position. So now one of the Cl para position will get substituted by the nitro group, right? So is it this position that is the nitro is getting, or is it the disposition? So I have told you that this is a symmetrical molecule, right? Because of the presence of symmetry here, guys, either way, if the nitro is attacking on this position, if the nitro is attacking on this position, both position will be same with respect to this particular chlorines. If you clearly see, if you just focus, third option, it is attaching to the meta position of this Cl and meta position of this Cl, and meta position cannot be activated because these both are orthopara directing groups. But if you can see here in the option number 1, this Cl is, this is the para position for this, and this is the ortho position for this. So that is why it is favorable position, right? So is it clear why the option number 1 is the correct one, not the 3? Any doubts, any queries, please ask. Is it clear, guys?
Yes, ma'am.
Okay. So is it clear to the girl also who is saying the third option?
Yes, yes.
Okay, okay. So this is the explanation. You can see also here. You can refer this. I'm going to upload the slides and the YouTube video. So just see them. Okay, so coming to problem number 13. Oh, sorry, 11. Problem number 11. The correct order of increasing the reactivity of CX bond towards nucleophile in following compound. Okay. Now they are asking the order of increasing the reactivity of CX bond towards nucleophile. So CX bond towards nucleophile means now there is a nucleophile which has to be added. There is an external nucleophile which has to be added on these positions, right? So now tell me the carbocation which is getting generated, the CX bond they are talking, that means this CX bond. The reactivity of CX bond will depend on the generation of the carbocation. Here also the carbocation is getting generated, and here also the carbocation is getting generated after the removal of this Cl, that is the leaving group. So they are asking that the correct order of increasing the reactivity of CX bond towards the nucleophile. If nucleophile has to add, the CX bond reactivity has to be mentioned. So here, after the removal of this chlorine, the leaving group, after the cleavage of CX bond, the positive charge is going to form at the carbon. So now the positive charge which is stabilized, nucleophile will attack it there, right? So nucleophile will attack on that particular carbon which is stabilizing the particular positive charge, having the electron density higher, right? So nucleophile will add to that species with where there is higher electron density. So now tell me among these four which is having the highest electron density?
3.
3.
3.
And the least electron density is with
First.
first or second?
Yeah, second one.
Yeah.
Second one.
Because it is attached to again electron
Electron
withdrawing
withdrawing.
groups. That is why it is also taking up the electron from the ring, so it is making it electron deficient for the nucleophile to add. So now what will be the correct trend? Third will be the highest, second will be the least. What about first and fourth? So third will be the highest, second will be least. Is it so? Let me see. So here the electron density is higher, so third will be the this particular option. And here this is the secondary, so fourth will be coming here, but this has to come here and this has to come here. So there is a correction, I think, in the particular option. So now because the nucleophile will add to that particular species which is less electron deficient, right? So here this first is less electron deficient than second, right? So here the option number C is correct one, but the second is going to replace the first, so there is a correction in this option. Okay, so C will be the correct one, but second has to be the least and first should be coming here.
મેમ ન્યુક્લિયોફિલિક રિએક્શન થાય તો નેગેટિવ ચાર્જ રિંગમાં થાય ને એટલે ઓપ્શન સી રેડી જ છે, કરેક્ટ જ છે, ચેન્જિંગ નહીં થાય.
एक सेकेंड, हाँ मुझे थोड़ा सोचने दो. एक मिनट, हाँ. Nucleophile has to add here, right? So negative charge has to get, negative charge is getting generated. But here is also a positive charge after the cleavage of this CX bond, as the question is saying. Okay, so here this option number C will be correct because second is okay. In turn, which is generating the negative charge, that negative charge in turn is also getting stabilized by the nitro groups. Okay, so they are talking about both the things. CX bond cleavage, and the negative charge which is now generating after the attack of nucleophile, uh, that has to be also get stabilized. That's why there is a two things which is operative here: the cleavage of CX bond, the positive charge generation, the nucleophile attack, and then the negative charge generation. So both things you have to think, right? So that is why option C is correct. So now,
Ma'am, option C follows SN1 mechanism. So Cl bond breaks by its own, whereas in second option it is aromatic substitution.
hmm,
So first nucleophile attacks, after that Cl bond breaks. So third is more feasible, whereas second and first involves attacks of nucleophile first to break the carbon and Cl bond.
okay, okay, getting your answer. But the thing is, I am just saying it a different way because I'm saying that positive charge is first getting generated, and you are saying that this nucleophile addition elimination kind of thing, which I am previously saying, right? Okay, but here also it is
Yes,
possible now. But what you are saying is possible in that first case also. It can also show the mechanism which is operative there, the nucleophilic aromatic substitution. So if it is following there, then you can say that first and second, in between those, second is stabilized then first, right? So here,
yes,
here
yes,
SN1 is operative, and here the nucleophilic aromatic
yes,
substitution is operative. Okay.
yes,
Yeah, very nice. Yeah, this is the particular thing which I am saying because here I am thinking about this SN1, but then also you have to think about the negative charges which is getting generated in the ring, because here there is no ring, the third and fourth part. So you have to worry about the positive charge only, but in first and second you have also a concern about the negative charge. So now the electron withdrawing group which is present on the ring will stabilize that thing more. Okay, that
yes.
is why the
In first and two, Cl bond won't break by its own
yeah,
because it has partial double bond character.
character, yeah,
Whereas in third and fourth, it can.
yeah. So that is why part C will be the correct option. Okay, so I hope it is clear to all of you.
Yes, ma'am.
Okay, coming to problem number 12. So now these questions are very simple, guys. I'm just adding this. So here they are saying that arrange the compound in increasing order of rate of reaction towards nucleophilic substitution. So as I've told you, nucleophilic substitution demands electron withdrawing groups or releasing group. What will be the correct order of reaction? Tell me what will happen. Nucleophilic substitution has generated a negative charge on the ring. And now just tell me the order of reactivity between A, B, and C, which will be the least reactive. What happened? You guys have answered already these things. Okay, let me answer. So here, in the nucleophilic substitution reaction, I have told you that what will happen, a Mesenheimer complex will form, nucleophile will add, and the negative charge is going to form at benzene ring. So if the negative charge is going to form on the benzene ring, which are the group which is going to stabilize this negative charge? Electron withdrawing groups, right? So now tell me which will be the less reactive, like least reactive species. A, B, and C. Which is least reactive towards a nucleophilic substitution? Anyone? Okay. So A is having the least reactivity. Why? Because there is no electron withdrawing group that are attached to stabilize the negative charge more. So here the negative charge is not going to stabilize with any of the further effect or any of the further group. That is why A is being the least reactive towards the nucleophilic substitution. What about B and C? What about B and C? If A is the least reactive and B and C, among these two, which will be more reactive?
B more reactive.
B will be more reactive because negative charge which is getting generated adjacent to Cl after the attacking of nucleophile adjacent to Cl, this negative charge is going to generate. So negative charge is directly stabilized by the electron withdrawing group that is present at the ortho position. But here the meta position electron withdrawing group is present, so that is why B is having the higher rate of reaction than C. So option number, which option is correct? So which option is correct? Option number, so option number third is correct one because A is least reactive, then C, and then B. B is having the highest reactivity order. So now coming to option problem number 13. So here again the similar question, which is more reactive towards the nucleophilic substitution. Which is more reactive? What is the trend of this particular nucleophilic substitution? Is A is more reactive, B or C? Tell me.
A. A is more reactive.
Yeah. Then B, then C. Why? Because the negative charge which is going to generate in the nucleophilic substitution reaction, here if it is stabilized by some means, but here it is getting destabilized because of the presence of electron releasing group. And two electron releasing groups are present. That is why it is less stabilized. So that is why A is more reactive, then B, then C. So A is more reactive, then B, and then C. So option number 3 again is the correct one. So is it clear, guys? Is it clear to all of you?
Yes.
Yes,
Yes,
ma'am.
ma'am.
Fine. Now coming to problem number 13. So this is some IR questions which I am sharing with you. So today's topic is somehow IR also. So I have just started 2 or 3 questions of IR. So these are some simple questions. So in infrared spectrum, that is the IR spectrum, which of the following functional group has the highest frequency? Is it ketone, aldehyde, ester or alcohol? Which is having the highest frequency?
Alcohol.
Alcohol. Why? See, I am just giving you a concept that frequency is directly proportional to force constant and inversely to reduced mass. So here the force constant, higher the force constant, higher will be the frequency. So here the highest frequency is corresponding to the alcohol. Okay, so is it clear? This is some basic question about the frequency.
Yes, ma'am. Yes, ma'am.
Okay. So now coming to problem number 14. Which of the following absorb IR radiation? Homonuclear diatomic molecule, heteronuclear diatomic molecule, both A and B, or diatomic molecule will not absorb IR? So what will be the correct option?
B. Option B.
Option B, heteronuclear diatomic molecule. Why? Because see, heteronuclear means having this a different atom present in the molecule. But if you talk about the homonuclear, that is oxygen, nitrogen, chlorine, having the similar kind of atom. So diatom containing both the atoms same. They doesn't have any dipole moment. And because of the dipole moment only, the IR stretching and bending is getting observed, right? So because you are getting the frequency because of the presence of dipole moment. If the molecule doesn't have the dipole moment, it will not going to absorb the IR radiations. So here, because of the presence of zero dipole moment, these are IR inactive. but H2O, HCl, NO, as they have the dipole moment present because Cl is more electronegative than hydrogen, and in each cases nitrogen and oxygen there is a electronegativity difference. So there is a dipole moment which is present in the molecule. So because of the presence of dipole moment, these are IR active species because molecule absorbs IR radiation. But homonuclear molecule doesn't absorb the IR radiation because of the net zero dipole moment. So that is why option number B will be the correct one. So heteronuclear diatomic molecule will be going to show you the IR frequency. So is it clear this question? Okay. So now coming to problem number 15. Now they are asking which of the following transitions mainly occur in IR? Which transition is responsible for IR frequencies? Electronic transitions, rotational and vibrational transition, rotational transition only, and all of the above. Electric, rotational, and vibrational. Which is the transition which is responsible for IR radiations?
B. Rotational and
Option B.
vibration.
Option B, rotational and vibrational. See, if there is only rotational transition, then you are not going to see the IR spectrum. But if molecule does rotate and vibrate, then it will absorb the IR radiation. Otherwise, it is not going to absorb the IR radiation. Okay, so is it clear?
Yes, ma'am.
Fine. So this will be the last question of this lecture, problem number 16. So now you have to identify the correct order of IR stretching frequency of the C double bond C bond, that is the olefinic bond between this like cyclohexene, butene, and cyclopropene. So exomethylene group having the higher IR stretching frequency. So you have to arrange them. So IR stretching frequency depends on the force constant of this C double bond C group. Okay. So now, depending on the strong and stability of this C double bond C, you have to answer the correct IR stretching frequency order. So can anyone tell me what will be the correct order? What happened? Okay. So guys, what will happen? See, I'll tell you what is the explanation for this. Because of the C double bond C stretching frequency molecule, there is a S character which is developed in C double bond C bond. What happened if you have a ring strain in the bond? See, these rings having some ring strain. According to the Bayer strain theory, cyclohexane, butane, and cyclopropane have some ring strain, right? So, depending on the ring strain, higher the ring strain in the compound, higher will be the S character. What do you mean by S character? See, if the S character is going to increase, then the stretching frequency also going to increase because there is a higher S character around this double bond. That is why the stretching frequency, that is the force constant, is getting increased. So higher will be the higher S character, higher will be the uh, like higher will be the strongness between C double bond C bond. Is it clear to all of you? See, here cyclopropane ring is having higher strain than cyclobutane ring, which in turn is having higher strain than cyclohexane ring. Because according to the Bayer strain theory, any ring which is having any ring having the less or higher the dihedral angle from 109.5, right? So higher the dihedral angle from 109.5 or less 109.5, then both the rings are straight, higher or lower. So this six membered ring is having higher because the angle between the CC bond is 120 degree. So that is why it is somehow strained. But the cyclobutane and cyclopropane ring is very much strained than cyclohexane. So here cyclopropane is having higher S character than cyclobutane ring and then cyclohexane ring. So here this double bond is much more stabilized or much having the uh, like you can say the bond length is shorter of CC bond in this cyclopropane case, and that is why the stronger the double bond, stronger will be the force constant, and here the stretching frequency will be higher. As I have told you, stretching frequency is the function of force constant and reduced mass. So here, if the CC bond is stronger enough, then the force constant between the CC bond is getting higher. So if force constant is increasing, then the stretching frequency is increasing. So that is why here having the higher ring stain will increase the S character, and that is why the force constant is increasing and the stretching frequency is increasing. So what will be the correct order now? Can anyone tell me?
Option 3.
Option 3. The third, second, and first. So third is having the higher stretching frequency, then second, and then one. So is it clear to all of you? Any doubts? Any questions? Anything which is not clear? So should I consider that you guys got the answer?
Yes, ma'am.
Okay. So if everything is clear, then I'm just closing this session now. So I'm done for today, guys. So this is much. This is enough for today. Sorry. So I'm closing the session now. So thank you so much for joining. And if you have any queries regarding any of the questions, just tell me now, and you can also comment on the YouTube video, or you can ask me in the next lecture, which is going to happen on next Friday, 6 to 8. Okay.
Thank you, ma'am.
Okay. So I'm just closing.
Thank you, ma'am.
Thank you, ma'am.
Okay. Thank you so much
Thank you,
for
ma'am.
joining the session.